Hey everyone, I'm Bram. I am the founder at Chia, and the whole approach to programming that is Chialisp is my conception.
Richard, you want to introduce yourself?
Sure. My name's Richard. 2/3 of us are named Richard tonight. I'm Richard Kiss, and I implemented CLVM and the first crack at the CLVM compiler, also known as Chialisp.
Cool. And I am Richard as well, but I'm going to be going tonight as efficient. I'm just going to be the QA moderator, and Bram and Richard will do most of the talking. So without further ado, we're going to start with sharing the presentation and get going. And here we go. Whoops, not that button. Sorry, guys. Let's try that again. Okay, cool. Okay.
So we're going to be talking about why we're doing things in Chialisp. Richard was actually the one who suggested using a Lisp-like thing. Initially, what happened is I had a bunch of notes about on-chain programming, and I was not very happy with any of the approaches I'd come up with. And Richard suggested we could use Lisp because that fixed the problems in the stuff I'd come up with. So we're going with Lisp. Whether this is like the epitome of, whether Lisp people think this is the epitome of Lisp or a completely demented take on Lisp, I don't know. I'm kind of curious to hear what they think. But it definitely has a lot of Lispy aspects. So we're not using Lisp as our on-chain environment just for the fun of it. Just to punk everybody with forcing them to do this, although that's certainly a benefit. There are some very direct, tangible benefits to doing everything in Lisp. If you essentially port something from Ethereum to Chia, the thing you have when you're done porting will be much better than what you started with. It will be a better thing, although it will be a bunch of work for you to make the transition because you have to have this different approach to programming in the Chia on-chain environment. But at a high level, the benefits to Lisp and CoinSet, as we'll see, Chialisp means very much. In fact, it's not obvious how to make it do anything at all, unless you're talking about the CoinSet model and going into specific tricks that you can do in it. So high-level benefits here are everything is extremely reliable and auditable. We are aiming to not have people, oopsie, I bricked $1 billion worth of wallets, trying to avoid those kinds of issues. Further, it allows for sandboxing. This is very important if you want to have, say, a colored coin being a good example of this, a token, because you want to enable smart functionality in your token without that smart functionality being able to reach outside of what's its business and cause new tokens to be printed. You want to make them be able to execute, but within a controlled environment where what they can do is limited. And you also want everything to be scalable. On-chain scaling, I continue to say, is not a good idea in the sense that you don't get cryptocurrencies to scale up just by cranking up the knobs on how many transactions per second the chain supports. Some cryptocurrencies have attempted to do that to their detriment and learned the hard way that that's not a good idea. However, if you can get a constant factor where good engineering has enabled you to do that constant factor while it's still possible to run a full node on a normal desktop, that's worth doing. Chia is scalable in that sense. So the first thing to know here is that we're in the coin set model, which is very, very similar to Bitcoin's UTXO model. So this is different from the account model. So in Ethereum, you have this concept of an account which has a balance, where in Bitcoin, you just have individual, they call them UTXOs, and Chia, you call them coins. And the life cycle of a coin is it doesn't exist, and then it's born, and then it dies, and that's it. That's the entire life cycle of it. It's not a persistent variable that has a balance associated with it. It has a size, it has an amount, it has this value that it's worth, but that doesn't change over time. The coin, the actual value of it is fundamental to the coin's identity. So here's this image shows an example of how this works, where you have really 3 wallets that have account A, account B, account C. And in the account model, each wallet has in its on-chain state just an account. And these have balances that vary over time. So this shows how the balances are varying on the right of this image. And on the left, it shows how you do it in the coin set model, where each wallet has individual coins that it controls, but the coins kind of have this separate life from each other. And so in this example, initially wallet A has a full 20, and then a transaction happens, and now wallet A has 12, and wallet B has 8. So that's pretty straightforward in both cases. Each one of them can have just 1 coin. Then something interesting can happen where wallet A sends a payment to wallet B of 2. So in the account model, this just nets out. It forgets all the details of how it got here. And you have 2 balances of 10. But in the coin set model, now wallet B actually has control of 2 coins. And wallet A might still have control of just 1 coin. But since B got 2 different payments, they have 2 coins. And then something potentially interesting happens here. So in this example, A makes a payout to C, and that just happens. And simultaneous with that, B makes a payment back to A. And in the example that's being shown here, something really interesting happens, which is the coin that's worth A simply disappears. And the coin that's worth 2 that B controls, that makes 2 output coins, one of which is worth 9 that B controls, another one of which is worth 1 that A controls. A very powerful thing that Chia payments do is whenever coins are made, they have a parent. There's some coin that made them. But the correlation between output value and input value isn't very clear. There's this rule that the total amount of output value has to be the same as the total amount of input value, but it's really normal for a coin that's small to make a coin that's big and gets balanced out by another coin just that's much larger than it simply going into the great beyond. And that's where the balances come from. That's an important nuance to what happens here that enables offers to happen and a whole bunch of other things. So there's a question of why we're using Lisp specifically, aside from the benefits I gave before. Lisp, first of all, it's extremely simple. The particular variant we're using here is, one might call it ludicrously simple. Believe it or not, it was even simpler before. We made some bends to practicality over things that we could have been really, really persnickety about. But if you have something that's consensus critical, where it's very, very important that all implementations of it behave exactly the same, being extremely simple is very, very important for that. It's also Turing complete. You can do general purpose programming in this very, very simple thing. And then it has no side effects, which actually, this is really, really important. Bitcoin's state machine is stack-based, and the initial notes that I had, I was very unhappy about because I didn't know how you can sandbox a stack-based language. That's just really, really extremely ugly to do under the best of circumstances. It can be done, but it looks like a bunch of hacked, bolted on things. And so we wound up going with this approach where we just take no side effects at all to enable sandboxing as a fundamental of what it's doing, just deep inside of everything that's part of the plans. And then also we have reasonable ability to call eval. That if you want to generate a snippet of code and run it, you can do that in a completely reasonable way in Chialisp. This is something that tends to be okay to do in Lisp in general. Eval is, extremely looked down on and bad in most of programming in general. And it turns out, as I'll get into later, calling eval is actually a really normal, reasonable thing to do when you're doing on-chain programming. When you get into like Taproot and Graftroot, both of these involve like, oh, here I'm going to pull out this snippet of code, and then I'm just going to run that snippet of code that I'm just given as a just normal thing that one does. So eval is a thing that's totally reasonable in Lisp type languages that simply not at all practical to do in any reasonable manner in kind of C style stack-based sort of languages. And related to that, it's very straightforward to do code generation because the data structures are so simple. You can make code in it, no problem. So now I'm talking about how simple and side effectless Chialisp is, or technically speaking, the CLVM is. So what we have here is there's Chialisp is kind of like Solidity. CLVM is kind of like the EVM. So technically speaking, Chialisp never runs on chain. Only this compiled stuff runs on chain. And other languages could compile into CLVM. And then we have also the what we call the conditions language, which I'll get to in a second. Normally, we just kind of refer to the whole thing as Chialisp, which is technically incorrect. But the really technically correct thing is to talk about the Chia on-chain programming environment. But if you just look at the CLVM itself, it looks like it can't do anything. Like you can go through this painful process of building up how to do stuff in it if you're clever, but then it's like, well, wait, but this is not what we want. We want to build like rate limited wallets and NFTs and a whole bunch of powerful things. How do we go about doing those? This is just like a difficult to use programming language. So that really gets into what the on-chain environment looks like, which allows you to build these things. And this is really something where it's kind of going in the opposite direction of what you would expect. A lot of people thinking about on-chain programming environments have started with the UTXO model and thought about adding capabilities to it. This is doing the opposite thing. This is taking the UTXO model and dumbing it down and simplifying it and tweaking the actual language in a way where it's capable of speaking self-referentially so that you can actually implement capabilities in it without having to add that as new functionality that's a property of the chain as a whole. So this is For those who know about it, this is vaguely along the lines of simplicity, although the simplicity environment does not change the format of transactions themselves. So this is not only simplifying the language in the same kind of way that simplicity does, but also simplifying transactions as well in a way that's very synergistic with that. So yeah, so Chia is based on the CoinSet model, which is a lot like Bitcoin's UTXO model, but kind of cleaned up in all the details. In Bitcoin, it's kind of like the first class objects are transactions, and coins are kind of like these side effects of transactions. In Chia, it's really that the coins are first class objects and the transactions are just these transient things that justify the creation of some coins and the destruction of others. Having everything be a coin actually is really, really nice because everything interoperates. Everything knows it's talking to a coin. It's kind of like in Unix, everything is a file. And having things be expressed as coins allows these programming tricks. So a coin has a parent, a puzzle, and an amount are the three fields of a coin. The puzzle being what in Bitcoin you call the script pub key. And then we talk about solutions, which in Bitcoin are called script sigs. So you can have the puzzle actually enforce things about itself. It can do logic about the format of coins. It can do logic about the format of puzzles. And so they can make assertions about what their parents look like, what their children look like, what they themselves look like. We have allowed them to do this in our conditions language. And we have also allowed coins to send messages to each other as part of how you program on chain to allow a lot of power in Chialisp. Further things that that enable this very simple environment to do a lot of powerful things. Our transactions all happen simultaneously. Instead of there being a series order in which everything happens, it's kind of like each individual coin getting spent makes assertions about other things that are happening at the same time, and they're literally all in parallel. And then the signature algorithm we're using is BLS, which allows non-interactive aggregation of signatures, which is also really convenient for taking multiple things and forcing them to happen together so they can't be separated out by others. So high level here is Chialisp is this very kind of like the Lisp equivalent of assembly that really doesn't allow you to do much of anything. And this way that coins work, the way that coins have this very simple format, which can be talked about and enforce things and has a hash chain history that can be referred to from inside of the CLVM and where they all get spent simultaneously. That's what makes it possible to do very sophisticated programming and have advanced functionality. So there are a bunch of things you might want to have here. So the most fundamental thing you might want to have is a singleton. In programming, singleton is a fancy word for global. But a singleton is kind of an identity that is persistent over time. Now, coins are not persistent over time. A coin is born and it dies, but a singleton is a soul that's present in a coin at any given time. So there will be this chain of coins that through their lineage pass down the identity of this singleton and can go through it. And this kind of acts like a persistent thing that other smart coins can know that they're talking to it. and it has logic that's persistent going down. So one of the most basic things here is pay to singleton. That's like there is this wallet or thing that's represented as a singleton, and I want to make a payment that can only be unlocked by that one singleton. It is a very fundamental thing across a number of different pieces of functionality you might want to have. Send a payment to this identity. That is actually used in our official pooling protocol to great effect. Another big thing that is enabled by this, that we currently have in prototype form, we haven't implemented it, we need to put some more polish on it, is non-counterfeitable tokens. That you have a colored coin, you have a fungible token as opposed to a non-fungible token that is divisible, it can be chopped up, multiple ones of them can be coalesced into something, but this represents a small amount of this, a small amount value of this represents a larger amount of something else, whatever that might be. And the functionality you really want out of these is that people can't counterfeit them. That in some sense, it's trivially possible to just make a coin that looks like it represents one of these things, but you can, using a little bit of programming cleverness, make it so that that's now not spendable via this trick of, in order to spend it, you have to show it stuff about its parent, and its parent wasn't the right form. Therefore, it's not spendable when you counterfeit it. And finally, among programmatic tricks that really add some power here, there are offers, which is a very, very powerful thing, where any two tokens in Chia immediately enable over-the-counter trades, that someone can make a partial transaction, not a full transaction. It doesn't quite work right. But what it tries to do is, for example, if it's an offer to buy some of a token for some Chia, it will burn a bunch of Chia and print a bunch of the token, which you can't do. You're not allowed to simply print tokens. But these can be bundled together. And now this can be sent to other people, and it acts as an offer. So other people can say, oh, I'd like to take that offer. I want to make that trade. And they make the other side of this. They make another partial transaction that prints a bunch of Chia. It prints a bunch of Chia and burns a bunch of the token. It does balancing amounts of both of those. So when you put the two together, they net out, and the amount of Chia and the amount of the token are the same as when they started across the two of them. And this is now a valid transaction that can be introduced to the blockchain. This doesn't have to require any interaction with whoever made the original offer to begin with. They sent out the offer, and they are now safe and secure in the knowledge that this can't be used to steal from them. It can only be used to accept the offer, which if the market exchange rate shifts too much, they could lose out for having done this. But that's the worst that can happen to them, is someone accepts the offer at a point where they'd rather have retracted it. And it's actually possible to market make. You can take a combination of a bunch of offers and put them together and take some of the spread, and that is still a valid transaction that will go through on the blockchain. Then you can get really fancy, advanced programming hacks where you can have automated market makers. So like Uniswap is an example of this, one of the most successful examples of this, that you have something that is an entity that just kind of sits on chain. It follows the rules where it works on chain. And it acts as a liquidity provider. It like pairs two different coins together. It has holdings of one type of token and holdings of the other type of token, or maybe just plain Chia. And then it will happily trade with people. It will make offers with other people, but only following its own business logic rules. And despite the fact that this doesn't actually have information about market conditions outside of itself, these have been quite successful and profitable in terms of trading. There's a trick to making these work really, really well, which is that tokens are so lightweight in Chia that actually an AMM can have its own internal use token that it uses. So when you make a deposit in the AMM, you get back out tokens that are the AMM's internal token. And those can actually be custodied and everything and be full smart tokens themselves. And then the AMM itself actually winds up being very simple, where it just knows the beginning balance of Chia that it has, the beginning balance of the thing that it's pairing with, and then the initial amount of its internal use token. And then it knows those three values after the transaction as a whole happens, and it's either okay or not, according to its business logic, with this transition of things. And then probably makes an announcement of what those are that can be used as an oracle. So as a price oracle. So that really enables a lot of power, that when you, even in AMM, when you have deposits in the AMM itself doesn't have to keep track of them. They can just be coins that are out there that allow for custody. You could even do really crazy things like make pairings of those to other things. I don't know if that would be a good idea, but you could do it. There are further advanced programmatic tricks you can do, that like a coin, that's a kind of a way of dodging around keeping all that much state in one coin. But you could actually keep an arbitrary amount of state in a coin, that you can have a huge amount of data and the coin hides it in its puzzle, or most likely a singleton hides it in its puzzle. It just remembers the root of this whole big data structure, and it has to be given the whole big data structure and go, oh yeah, that's it. And that data just appears transiently while transactions are being evaluated, and it goes right back to just being a normal coin afterwards. And it's possible actually to make it so that if you want to keep the costs down for that, it can be that there's a whole, that it remembers the root of a Merkle tree of something. And whenever it needs to be proven information, when it wants to do a lookup of its own data, it's given a proof of that portion of its own data as just a path through the Merkle tree. So it's just enforcing what that part is. And if it wants to update the data, it is given the path of all the side branches of the parts that aren't being updated, so that it can validate, yep, this is updating the way I want it to update. That's another very powerful programmatic trick that enables all kinds of things. Although to date, we've actually successfully avoided needing it. So maybe you don't need to do that very often. All right, now I'm going to hand this off to Richard, who's going to get more into the nitty-gritty of actually what Chialisp actually looks like.
All right, thank you, Bram. I like to say CLVM is what would happen if assembly language and Lisp had a baby. It's got some properties of both its parents. It's kind of cryptic and unreadable like assembly, but it's got the magical data structure of Lisp, namely the cons box. Like most Lisps, CLVM has a base object, which can be either a cons box or an atom. Normally Lisp has all sorts of different types for atoms, like you might have a floating point type or an integer type or a string type. CLVM only supports, for atoms, a list of bytes, so a binary blob. And you can interpret that in different ways. You can interpret it as a number, or you can interpret it as a string, or you can interpret it as a public key, because all these things can be encoded into bytes. And so that's what we do. we encode these values into bytes and then operate on them as bytes. So an atom is the very simplest form of a CLVM data structure. It's just a string of bytes. And then this is the alternative CLVM object. If it's not an atom, it's a cons cell, which I like to call cons box. And a cons box is essentially an ordered pair of CLVM objects, which means that it's got a left and a right, or a first and a rest, we like to say. And each of these elements can themselves either be an atom or a cons box. So this ordered pair gives you all you need to make recursive data structures. It's the very simplest form of a recursive data structure. I like to say it's the minimum you need to be Turing complete. So now let's talk about the representation of cons cells. Actually, let's go back for a sec. We're spoiling the surprise. I'm just kidding. If you take a look at the quoted value, q.100, that is an ordered pair where the first object is a q, or it's actually the opcode for the operator q. And the second object is a string of bytes, which represents the integer 100. All right, that's enough. Let's go to the next one. Sorry, I just wanted to mention that. Now we're talking still about representation of data structures. A list is a special case. A cons box can be written as a dotted pair, but we turn this dotted pair into a list using the mechanism you see on line, I guess 1, 2, 3, 4, or 5, 100.200.300. Empty parentheses. That can also be written as 100, 200, 300. So that's a list of 3 items. And you can see clearly how this generalizes to arbitrarily lengthed lists. Arbitrarily lengthed lists. That's quite a tongue twister. And you can see that lists can also be nested. So you can get extremely complicated or arbitrary data structures. And I like to think of cons boxes and CLVM objects as trees. So if you look, here are 3 examples of cons boxes of varying degrees of recursion. On the left, you see 100.200, where the top node is a cons box, and then the left is 100, and the right is 100. And then the second example is 100 on the left, and then another cons box with 200 on the left of it and 300 on the right of that. And then the third example, which is the list 100, 200, 300, this is how it looks in tree form. And you see this pattern a lot where your tree is very right heavy because the first thing is an atom or something small, and the rest is the thing on the left, which is the first, is an atom or something small. And the thing on the right, the rest, is more elements to your list. So a list is sort of the base structure that CLVM programs use. So what is a program? Well, in CLVM data structure, the only data structure you have is a cons box, which, as you've seen, can be adapted into arbitrarily length lists. And a CLVM program is just a list, or is just a CLVM object. If it's a list, then the first element in the list is an operator, and all subsequent elements are arguments to that operator, but they themselves have to be valid programs. So you get a nice recursive definition. And when a program is running, it has an environment, essentially its list of local variables. And that environment is itself a CLVM object, which means it's an atom or a cons box and potentially recursively contained an arbitrarily deep tree. Now, a single atom can also represent a program. And in that case, it's a little optimization which drills down through to the tree. So a one gives you, a one is a program which returns the environment. A two by itself is a program which returns the left side of the environment. A three is a program which returns the right side of the environment. A four is a program that returns the left side of the left side of the environment, and so on. And this can be arbitrarily deep. Now, if you look at this tree, the numbers do seem a little scrambled up, and that mostly has to do with implementation detail and trying to keep the implementation of how we follow down the tree very simple. Essentially, you look at the low bit, and then you go left if it's 0, right if it's 1, and then shift, and then repeat until you get to 1. Next slide. So now let's do a little live demo. There's a tool called Bram, which I want to show you. Can we switch to the window? Okay, so first thing, I want to create a virtual environment. Oh, that's interesting. What's happening? We have Python installed? We do. Oh, I see. Python 3, that's what we want. Sorry, guys, it's my first day. Okay, and I like to soft link activate.
Richard's a comedian.
Let's get rid of my failures there. Now let's install CLVM tools. This gives you a couple good tools, including Bram, which was my favorite. Here's a very simple program which simply quotes the value 100 and returns that value. So, okay, that seems great. That seems fairly simple. And then here is an operator running on that value 200. And well, when you add 200 to nothing at all, you get 200. So let's throw another number in there. We get 500. Most of the arithmetic operators are represented. There's multiplication. Once the numbers get too big, they actually turn to hex. So let's make them a little smaller. Because when it operates, it doesn't actually know what how you want the value to be displayed. So it just uses some heuristics. I think if it's more than 2 bytes, then it starts to display it as hex. What else do I want to talk about? Let's run. Okay, let's look at this. You'll see that error message a lot when you're working in CLVM. So what this is doing is it's quoting the cons box 2030, and 20 actually represents div mod. So let's make it 200 so that, because 200 doesn't actually represent an operator, so it knows exactly how to display it. And if we take the first thing from here, then we're going to get our 200 back. And if we take the rest, we get 30 back. So let's go back to the slide. I think there's some notes on the slide on what else I wanted to show. Oh yeah, okay, so this is the exhaustive list of operators that Chialisp supports. You can see the first line, those are the core operators, and those are a little bit of Maxwell equations magic, that with just those 8 operators, you can you now have a Turing complete language. And then once you add the string operators, now you can operate on strings in an efficient way. When you add the integer operators, you can operate on integers in an efficient way. And then when you have the Boolean vector operators, you can do logical operations like AND or XOR. That's all masking. And then log not, which is like XOR with -1, essentially. And then there are BLS operators, which operate on signature type stuff. There's point add and pub key for exponent. And then a few extra Boolean operators. These names come from Python, not any and all. And then there's one mysterious operator, which isn't too relevant yet, but will be in the future for soft fork. Next slide. Okay, so we've looked at Brun, which what happened? We've looked at Brun, which operates on assembly language. There is a corresponding tool called Run, and this operates on the high-level code. I'm an old Apple II hacker, so these names actually come from DOS 3.2, DOS 3.3 on the Apple II, where Brun runs a binary file and Run runs an AppleSoft program or an integer basic program. And when I was creating these tools, I used these names and they just stuck. So hopefully Apple won't sue us. Let's go back to the screen and I'll see if I can write a high-level program.
People in chat are asking, in Q&A are asking about loops a lot.
Oh, about loops?
Yeah.
Yeah, that's tough, but this will give you an example. So I'm going to try and write the Fibonacci function. If we only have one of greater than or less than, I can't remember which one it is. Where is that list of operators? This is how you keep your language minimal, is by only having one inequality operator. Okay, so if n is greater, or if 2 is greater than n, we return 1. Otherwise, we return the product of fib minus n1 and n. Okay, there's one paren, there's another paren, there's another paren. And what does that match? Paren matching. Okay, we need one more, and that completes the defun. And then we go fib n. And I forgot the closing paren. What a surprise. Okay, so now Run applies a transformation from the high-level Chialisp language and produces assembly language output, which, as long as I didn't make too many mistakes, should actually produce something. 1. That's not right.
Writing raw CLVM is pretty fiddly. We usually do Chialisp and then and that compiles into CLVM, which is much easier to do.
Oh, this gives us a chance to use the symbolic debugger. Okay, so everything is returning 1. Oh, and Fibonacci is taking 2 operands for some reason. Okay, so I see what's wrong. Yeah, one of these parentheses goes here because Fibonacci doesn't deserve 2 operands.
Lisp, by the way, is an acronym for lots of insidiously silly parentheses.
And they rarely balance. Okay, that's a little better. Factorial of 5 is 120.
Yeah, there we go.
These all look good. And you can see now that's also working. Let's try it with some really big number to show that it really does. So that, I actually don't have Fibonacci 15 memorized, but all the ones that are in decimal, I do recognize, so I think it's working. Okay, let's go back to the slides. There's that was the recursive example we just did. So for those of you asking in chat about whether this language really does have loops, yeah, it does. It's just you can only loop through recursion. And in fact, the implementation uses this fairly sneaky trick to avoid using the native CPU's stack, because we were worried about blowing the stack. So instead, it allocates its own CLVM stack on the heap. Because CLVM does support recursion, you can, in theory, the halting problem enters, and you can, in theory, write a program that never finishes. So the way we work around that is every operator has a cost, and while we're running the program, we keep a tally of the costs, and once it exceeds the maximum cost allowed for that program, we halt and fail. So that's the hack for fixing the halting problem. Is Ethereum? I mean, Ethereum did it first with gas, and we do the same thing. And so here's an example of a contract. This is the standard what's it called? Pay to public key or pay to delegated puzzle or hidden puzzle, but it's also known as a standard transaction. So well over 99% of all existing transactions on Chia are of this form, probably, and most of the rest are probably singletons. You can see this is a module that takes 4 parameters: the synthetic public key, original public key, the delegated puzzle, and the solution. And then it defines an assert macro. And then it includes condition codes. Those are just some constants. Next page. And then it defines a function called SHA-256-tree1. This is used to calculate puzzle hashes. So it turns a CLVM tree into a puzzle hash. Next slide. And then this is an inline function, defun inline, which is similar to defun, except for it just expands it in place. So in some cases, defun inline is more efficient than defun. In other cases, it's not. And in, for example, recursive cases, it's impossible to inline your function. You couldn't write an inline version of factorial because there's no looping construct besides recursion. So this function, and here's another inline function. That's okay. You can see that this uses some functions, some of the other functions like is hidden puzzle correct and assert. Next page. And then this is the main function, which gets past the arguments that were declared at the top at the mod and returns the conditions, which we haven't discussed yet, but you'll learn more about later. And one interesting thing about this piece of code is it is essentially the Bitcoin equivalent of Taproot and Graftroot. So Chia had Taproot before Bitcoin, and Chia had Graftroot before Bitcoin. Bitcoin is just about to get Taproot. I think it's activated and will be a valid transaction in the next few weeks. But Graftroot, well, who knows? We'll see.
Yeah, we're a little ahead of the game here.
So besides the standard transaction, which is used by almost everyone, we've also shipped singletons and pooling. You have anything to say you want to say about this, Bram?
Yeah, we dog fooded pretty heavily on pooling. It uses singletons, it uses pay to singleton. It actually resulted in us having a standard format singleton, which we're planning on using on other things as well. But there's more stuff coming up. We don't have a standard token yet. So
we're still learning about CLVM, even though we made it. We only have a few months to years head start on most of the rest of you. So, and this is what's coming. Bram, why don't you take this? Because
yeah,
you know more about this.
Currently we're things that we have prototyped but are cleaning up are DID wallets. So DIDs, the main functionality we have in them right now is account recovery, which differs from sending shares to others because DIDs that have themselves gone through an account recovery can participate in the account recovery of others, even though they probably would have lost their shares that they had been sent if they were just implemented that way. Also doing colored coins for tokens that enable offers and everything, and rate limited wallets. All of these are things that we have built and are to be fully functional and are somewhere between, we broke them when we made a few final changes for mainnet. So they worked in the old testnet, but they don't work in the mainnet. And also maybe we want to rewrite them using more knowledge of how to write in CLVM that we've gained over time. And we also just need to add UX and polish them up and stuff. But these are all pretty close to functional, and we'll be refactoring them to be things that we're proud-ish of and making them available soon.
Oh, by the way, I kept saying Fibonacci, but it's actually factorial. I do know the difference.
I kept saying before that we'd get into conditions, but actually this would have gone way too long had we gone into that. So have to talk about conditions another day.
Yeah, conditions are cool and they're important, but I think some of the other videos talk about them. So. So I guess so. This is what's coming up. Should we go to Q&A?
Yeah, there are other tutorial videos people can watch that we've put up now. So those go a lot more into detail about a lot of these things.
Okay, so for those who are new to Zoom, there's actually a QA button, and you can that opens up a little window and you can actually type your questions, and I'll read them out and have either Bram or Richard answer. Some are trolley questions, so I'll leave the trolley questions to the end because you know, we like trolling too, so we'll take a stab at it. So the first question is, what is the importance of sandboxing, and is Lisp similar to Haskell?
I don't know Haskell, so I can't answer that.
Lisp is much older. Lisp is from the 50s.
Yeah, is Haskell a Lisp family language, or is it Ada family?
I think the draw for Haskell is it's purely functional.
Okay, yeah. So
they do a lot of currying and whatnot.
Okay, yeah. So then the short answer is yes. Haskell is in the same family as Lisp, where Lisp is the great grandparent of everything there.
Yeah, it's definitely a lot closer than, say, C. I don't think they have cons boxes in Haskell though, or at least not as such a core atomic unit.
Sandboxing is important so that you can have untrusted code when you're calling eval, when you have like intelligence in a singleton. It's very, very important that this code, that the thing that's enforcing, like that the balances of the token always stay the same, or that the singleton only exists once in the world. Those need to be enforced while still allowing for arbitrary inner puzzles, allowing smart functionality to happen inside of things. So,
And also for telescoping solutions like graphed root.
right, yes, yeah. Related to that, it makes it so that you can have like the hash of a, well, that's for eval, but we're talking about for sandboxing. Why sandboxing specifically is important. It's because
sure.
you often want to run untrusted code on chain as just a normal thing to do. And it turns out sandboxing is not something you can bolt onto a programming environment. The entire thing, down to the bare bolts, needs to be written from the ground up with sandboxing.
Oh, I was thinking of sandboxing within Chialisp, or CLVM, but you're talking about sandboxing CLVM from the outside world.
Yeah.
I see. Okay.
Okay. The next question is, can offers be set to be time limited or have some other conditions?
Yeah, sandbox offers can do whatever you want. They can have arbitrary conditions. One good example is there might be a price oracle that they rely on. So they want to trade a set amount of thing A for market rate amount of thing B, and they require an announcement from a singleton that is the price oracle to tell them how to do that, or to tell them what the current exchange rate is. That is a totally normal thing to do with offers.
Cool.
I don't think you can actually withdraw an offer, though. I think the way you withdraw an offer is you spend the coins yourself.
Yes.
Okay. Next question. As more Cheerless applications come online and get used, how do you think the blockchain size will grow? How much state is stored on chain? Will we get similar issues that Ethereum has with massive blockchain size, making it very hard to run and sync a full node, especially on low power devices? Anything in the design to reduce this issue? I'll repeat any parts of the questions you need.
Yeah. So the short answer is that the capacity of the Chia blockchain is 4 times what Bitcoin's is. So roughly speaking, might, once it starts getting full all the time, grow several times as fast in terms of raw size as the Bitcoin blockchain does. So Bitcoin supports for vanilla transactions about 5 per second. Chia supports about 20 per second. Ethereum supports about 10 per second. Ethereum requires a lot more infrastructure than just a desktop to run, requires much larger databases to keep track of what's going on, thanks to a whole lot of bad engineering. In Chia, the state is constantly collapsed down. So what happens in Chia is while something is being run, it has all this state, and then it's actually kind of analogous to PHP, that when it's done with whatever it's doing, all its state is blown up and disappears. So it makes a whole bunch of state that you have to ephemerally create during validation of the blockchain. But in the end, all that happens is that coins are created. So it has, the coin set can grow, dust can pile up, things like that, like happens in Bitcoin, but it's not, it doesn't grow in the same kind of way that the Ethereum on-chain state grows at all, like not even slightly.
Yeah, I'm not an expert on Ethereum, but my understanding is that it's a von Neumann machine, and every contract has some memory space that it can write into, which means that it can grow arbitrarily large. And that really can't happen with Chia, because the only state for a coin is its puzzle hash, which it's just a hash of potentially a Merkle hash of arbitrarily large amounts of data. But since it's just a hash, the solution, when you spend the coin, does the reveal for the parts that are relevant. And so it's very transient and much easier to control. You don't have to swap.
You can wind up having a number of coins, but you pay for them. It's very expensive to make coins. Very, very cheap to have this transient state that disappears really fast. My expectation is that eventually, just for sanity, there will be some kind of a soft fork where coins that haven't moved in like 100 or 200 years get frozen, but that's after my shift.
Yeah, so the short answer to the question is I hope that won't occur. I've tried to synchronize it. I've tried to do a sync of Ethereum blockchain, and it just got stuck at this certain period of time when there were all these DOS attacks. And it just never got through it.
Yeah, I think 1,000 years from now, having software without lock things that haven't moved in too long might be okay. But
Okay. Next question. What programming languages do you recommend someone who does not have any programming experience start with before diving to Cheerless?
The canonical language for starting on Lisp is Scheme. Chialisp is actually a lot simpler than Scheme. So you might want to just get started directly on Chialisp itself, but if you really want to start with a vaguely more mainstream language, Scheme would probably be the way to go.
Okay. Do we have an on-chain transaction to merge two coins or split a coin into two even if we don't change the total amount our puzzle hash inside all the coins?
Yes, yeah, that is changing your state, and that always requires an on-chain transaction.
Okay, so this is a follow-up on the recursion. So writing loops is the area for Chialisp developer, but please note recursion consumes stack memory. Windows has very limited amount of stack memory.
Yeah, we're not using the native stack. We are using our own virtualized stack. So you don't have to worry about.
CLVM uses a heap stack.
Yeah. The limitations on how much transaction you can have are cost limitations. So in the interest of consensus, it's very, very important that different things evaluating the same block will puke out on things having gone into an infinite loop at the exact same place. So you don't have differing opinions about whether something is or is not a valid block. So we took great pains to make sure that there's no weird random artifacts of the limitations of the particular machine doing validation that creep into that.
Right. That's one reason there are so few operators and so few data types.
Cool. So this is actually a legitimate question. We forgot to mention what mod is.
Well, that stands for module. So that's that means here comes some functions, and this is going to be a puzzle that goes into a coin.
Cool. Follow-up of, can you please talk more about the cost to run smart contracts in coins more? Here we don't have state, so will that cost more to run a program than like in ETH?
The way the costs functions work is you're paying for kind of three different things. There's size of stuff on chain, the size of the transaction that you have. There is coins that you're making, and there is CPU costs to run the whole thing. And the way, which actually that last one tends to be dominated by AgSig, aggregated signature verification. The way the costs are pan out, a vanilla transaction winds up spending about an equal amount on all three of those. So you could have transactions that are weighted more toward one or another thing. As it turns out, the computational cost of ephemerally doing computations and logic there and things are super, super tiny, like almost nothing. So generally speaking, transaction costs are dominated by the secure hashes that you're having to present on the blockchain, which you pay for because that's making those things big. The cost of making coins, because we want to disincentivize generation of lots and lots of dust. Like it costs something for full nodes to keep track of the unspent coin set. And then there's checking of the signatures, of the BLS signatures. Tends to be most of the computational cost on normal things that you do.
Cool. Okay, what's the process like to migrate Solidity smart contracts to Cheerless?
You don't verbatim, you wouldn't transliterate a Solidity smart contract to Chialisp. You kind of have to put it in this new framework where instead of like it being a contract that keeps track of this whole big state and does stuff, it's a coin or set of coins that work in a certain way. And the first thing that you do is you recontextualize, you reformulate, you put it into this different paradigm of how you think about doing things and then re-implement it there. So you do not generally speaking transliterate. Like doing AMMs is a good example of that. So once you're done doing an AMM in Cheerless, it's a much better AMM. It's much nicer to deal with and work with. It's much more powerful, but it requires that you rewrite it in this rather different way.
Okay. Is there an API to get block height or time? Because I think HTLC, which is hash time lock contract, needs to read the time.
There's no access to any oracles of any kind in Cheerless, but you have conditions. So what happens is instead of so your intuition in the question is, hey, I want to be able to say within my Chialisp, ask some oracle, what is the current block height, and assert that it's blah, 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 right? That's not how it works. The way it works is actually pretty analogous to the way time
check block time
Bitcoin actually. Your puzzle returns a list of conditions. One of the types of conditions that we have is assert that I must be this old, and it gives an age, right? So it itself is never told what the current height is, but the coin can make a requirement, or the solution can make a requirement that it must be at least X old in order to be spendable, just in its conditions. There's this short list of operators that Richard went over. There's also a short list of condition types that we have that include creating outputs, making announcements, requiring announcements, require a signature be in the aggregated signature, requiring your own ID be a particular value, and requiring the time be at least this amount, and requiring your own age be at least this amount. Oh, and having a fee. I might have missed one or two, but kind of a short list of things there that you can require of the world, but you can't ask for something and make assertions about it. You can only specify what your conditions are, and then the world figures out whether they're met.
Yeah, Bitcoin HTLCs use check lock time verify or check lock time verify or something like that. And Chia has something very analogous to that. It makes sure that a coin is at least this many blocks or this many seconds old before it can be spent again.
Yeah, the way Bitcoin does it is actually pretty hacky and special case for relative time locks.
It's extremely hacky.
Yeah, where we have it in this more generalized framework of conditions.
Okay, is there an IDE for Cheerless?
No, we are improving our development tools as we learn how to do a lot of this stuff ourselves. So things will improve in the future. And we really, really want for there to be a big ecosystem of developers around this, where it's not just us making everything. We are working on prototypes to show people how things can be done, and are hoping that there will be a much broader set of tools that are maintained by others, not just us.
Okay, do you anticipate a significant migration of existing ETH sidechained dApps to the Chia blockchain?
We think there's going to be a lot of certainly analogous things that we're going to have, AMMs and stable coins and all that kind of stuff. Presumably a fair number of projects that have their own token will want to do tokens in Chia just because the custody is so much nicer for them. As for particularly specific dApps that are on Ethereum, whether they might want to or are able to port over, that's, that's kind of up to them.
Okay, this is for Richard. Richard just said the way to retract a public offer is to spend the coin yourself. How does the public know the offer is retracted?
Block Explorer, that's one way.
Yeah, the coins are spent. It's pretty obvious.
Yeah, I mean, if you try and fulfill the other half of the offer, it'll just fail. Let's say you're doing double spend.
Okay. Can Richard explain again how Cheerless works around the halting problem, how it differs from ETH or doesn't differ from ETH?
As I say, I'm not an expert on Ethereum, but I suspect they do it the same way. They have a gas limit for your contract. When it exceeds the gas limit, the contract fails. And it's a similar thing with CLVM. The CLVM has a maximum cost, and when you exceed that maximum cost,
there's a big difference with I'm going to simplify just a little bit here. In Ethereum, you don't know what something is going to cost up front, right? You have a transaction that does stuff and it can look stuff up, and depending on what answers those things give, what its cost can be varies tremendously. And then you can have things that actually fail when they try to run, which still gunks up the block that they're in, but they get most of their gas back for doing that. Chia isn't like that. In Chia, there's just a block limit and that's it. It's a flat block limit. And they're like each individual transaction, its behavior is completely canonical in terms of how much it costs. And if a block as a whole is under the cost limit, it's good. If it's over, it's bad. And there's none of this like, oh, well, try it and see what it does.
Okay, currently the coins are stored in a SQLite database tables, and will that be able to handle the growth in coins?
Yeah, SQLite can actually scale up pretty well.
SQLite is amazing. I recommend reading up on it. It's really ridiculous.
Okay, it's another IDE question. It asks, is there a VS Code extension?
I think so. I don't know much about it.
I know there's somebody in the community wrote an Atom extension, so you can look that up. And one of the videos covered using that particular extension. So, okay, next question. How are wallets created?
Wallets created. Well, I'm not sure exactly what the scope of the question is.
Okay.
We have a number
How
of...
do developers create wallets, or?
I'm not sure. That's if the person can type more additional context in the following question.
Yeah, a wallet is a client side, application. If you mean how are wallets that do stuff developed, there is this funny thing where each type of smart functionality requires new wallet GUI to support that smart functionality. And we don't have a particularly great way of generalizing that right now. At the moment, we kind of custom implement each of these for each new bit of functionality. We kind of have these plans to make it so that you can write portable like snippets of JavaScript that can serve as the UX for a particular type of wallet that other wallets can include verbatim, so that if you make new smart functionality, it's easy for other wallets to support it.
Okay. With all these recursions questions, does the VM optimize left recursion? Is that a preferred pattern?
There's this notion of tail recursion, but no, the compiler doesn't optimize that, and I don't think there is a way to optimize that for CLVM.
Okay. You could rewrite everything where lists extend to the left and atoms end on the right. Our conditions language doesn't work that way, but your internal logic, you can make it work that way if you feel like it.
Can you elaborate?
Yeah, that'd be a lot of work.
Yeah, if you really want to write code upside down, I mean, more power to you.
Can you elaborate more about the offers programmatic hack? Do both sides of the transaction need to occur at the same height to be valid to go through, or can it be somewhat asynchronous?
No, they need to be smushed together, or it's totally invalid.
Okay. What could be expected that the Chinese tech community manager will be on duty? Okay. It's not exactly a question for this particular forum, but what I'll say is this: he's just started. We're going to get up to speed, but part of that is helping interface with the development community as well. One of the first things he's doing is actually getting the Cheerless videos, that training videos that we've done. He's going to work with a couple contractors to get it translated to Chinese, so you guys can see in your native language, at least in subtitling. So outside of that, we can answer that question in a future AMA. Okay. How are offers matched? I think we talked about that already. In near future, any plans to implement actor model like in Erlang?
I don't know that design pattern, so maybe Richard does.
No, I'm too ignorant to comment on this. Sorry.
Okay, sorry. Next, what are some possible and/or preferable methods of monetizations for developers?
Well, we think there's going to be a whole big ecosystem here. So there are pools. There are going to be wallets. There are going to be exchanges and AMMs. There's going to be all kinds of stuff. And most of those will be like actual, I mean, there's going to be integration work happening. There's monetization behind all of those things and all the normal ways.
Okay. If offers are recorded on the blockchain and decentralized exchange is realized through offers, won't that create too many transactions?
When offers go through, you do pay their cost. So they're not when a bunch of offers are put together, they do all hit the blockchain as a whole. So they're subject to the block size limit.
I think that eventually those trades will move to Lightning once Lightning supports.
Yeah, there's going to be payment channel stuff on Chia. That's way down our list of stuff to work on. We'll get to it eventually. Lightning's come a long way. I'm not super familiar with exactly what the latest and greatest of how they actually do everything in Lightning is. I did some thinking about it before and basically reinvented how to do Lightning on my own. And there's a bunch of things where there's different ways of going about doing them, where I'll have to consult with the people who are actually doing Lightning about what the current thinking about best approaches to things are. We're trying to create the problem of scaling before we actually work on fixing it.
That's legit. Is there a plan for lightweight non-full node wallets for Chia?
We have lightweight wallets in Chia. Our wallet really wants to run a full node because right now there's a lot of people are running farms, right? It's a pretty good idea if you're doing a farm to run a full node. You can run just a lightweight wallet and it will just talk to whatever full nodes are out there. We can probably improve the UX on that quite a bit. And also we're working on, right now we have this kind of, I don't know what's it called, old school Bitcoin style wallet protocol where you have to download not whole blocks, but a lot of filters and stuff. And we're moving towards a more Electrum style protocol, sort of. It's kind of partway between, but closer to Electrum than old school Bitcoin, which will make
faster.
It'll make it so that syncing is super quick. You just wake up and start talking to full nodes and you're pretty much done. Okay. We've seen the difficulty rate get harder. A few months ago, 1,000 plots could generate more than 10 coins per month. Now it's barely 1 coin. Will you see an improved difficulty where we can get more coins per 1,000 plots? It's not exactly Cheerless related.
Yeah, no. I predict the opposite, that work difficulty is going to continue to go up. It's been pretty steady of late, but no, I think in the future, we're going to see net space grow considerably. And yeah, profitability per plot per month is going to keep going down. Yep. Okay. Is anybody working on implement? I'm not reading that one. Sorry. I know Cheerless has major clear benefits, but given the difficulty of coders implementing it, can you foresee a world where another language atop CLVM overtakes Cheerless the way Solidity overtook Ethereum Lisp? Maybe. Like if other people want to make competitors to Chialisp that compile to CLVM, I mean, go for it.
I agree. Go for it.
Okay, so Here's the trolley question. P equals NP, question mark.
Yeah, sure.
I'm going to say yes.
Okay, that's it. We have gone through all the Q&A. This is not the only Q&A left. As Bram has mentioned, we have new training videos that just got put up today. Please feel free to look at them. The people who actually made those videos will have Q&A sessions available the next 2 days. You can find that exact calendar of when they're going to have the Q&A sessions on chialisp.com/training. And we try to basically make sure that we're actually a Q&A session for every possible time zone coverage. So hopefully you can find one that works for you. So with that, thank you very much for coming to the first kickoff on why Cheerless and with Bram and Richard. And thank you for everybody coming tonight. And we'll look forward to seeing your projects on the Chia blockchain very soon. Have a good night. Bye all.
Thanks, everyone.
Hi, everybody.
Bye.